Hello, everyone. I hope you guys are ready for this presentation. It's going to be great. A very warm welcome back to Workshop Wednesdays with Mentor Me Collective. I hope you have been well. Continuing our journey through September's theme, Shifting Gears in Automotive Tech, we're exploring the cutting edge innovations that are truly transforming the driving experience. For those of you who are new to Mentor Me Collective, we're a community dedicated to empowering individuals, especially first-gen techies, with the knowledge, skills, and tools they need to succeed in their tech careers, while also highlighting the positive impact that technology can have on our lives and communities. Today, we're navigating the most transformative frontier in the automotive industry, real-time decision-making in AVs, the hidden complexity behind simple driving tasks. Self-driving technology is no longer a sci-fi concept. It is a rapidly advancing field that promises to reshape urban mobility, improve safety, and fundamentally change our relationship with transportation. This session will move beyond the headlines to explore the core technologies, monumental challenges, and ethical considerations behind autonomous vehicles. We'll uncover how engineers and innovators are building complex software and hardware that allows cars to see, think, and drive on their own. Now, let me introduce our exceptional speaker, Edozie Eze. I'm just going to bring him up on stage. Hey there, how's it going?
Hi, Griselda. How are you?
Good. So, Edozie is a leading autonomous systems engineer and innovator with extensive experience in the research, development, and deployment of self-driving technology. With a strong background in robotics, machine learning, and computer vision, Edozie has been at the forefront of tackling and um, the intricate challenges of building self-reliable autonomous systems. He is passionate about the potential for this technology to create safer and more efficient future for transportation. He is dedicated to sharing his expertise to help others navigate this complex and exciting field. Edozie, before we get started on this vital topic, I'm gonna break the ice a little bit with a question. If your team is or was designing a self-driving car, what is one imaginative contribution someone could make that would completely change the game?
That's a great question. First of all, thank you so much for the introduction. Happy to be here. Thank you for the opportunity to speak to this group and help share some of my knowledge. Be looking forward to the next hour or so. To answer your question, I think there are a number of things, but one that comes to mind would be on the user interface, right? So uh, most people don't know why an autonomous vehicle, or what most drivers and passengers don't know why the
Mhm.
autonomous vehicle does what it does,
Yeah.
right? So if you, as an example, if you get into a situation where the car suddenly brakes or steers or stops, a lot of people may not know why that happened in that time, even if it is for legitimate reasons,
Mm.
right? So what that can do is, it can cause anxiety, it can cause fear, and erode some trust in the system. So I think creating such a UI system that tells you exactly what the AV is doing and why it's doing it,
Mhm.
I think that would be a game changer, because it would build more trust in the system, which is something that you need in any not just AVs, but any automated system.
Yeah, that's reasonable. I like it. Thank you so much. All right. And now let's hear from you, the audience. In the chat or in the text box, however you like to communicate with us, what's one everyday task you'd be most excited to have in autonomous vehicles? What do you want those kinds of vehicles to do? For you, just share that in the chat. We'll see your comments. And Edozie, we are so eager to hear your insights. Please share your screen and guide us through the fascinating world of autonomous vehicles. Over to you. I'll bring up your screen and I'll take myself off. All right.
Thank you, Griselda. All right, thank you all. I assume you can all see my screen. Again, my name is Edozie Eze. And as Griselda mentioned in the intro, I'm here to talk about decision making in AVs. So the meat of the presentation today is going to cover a number of things, which we'll get into. And it's the aim is really just to help you to understand how the things that we do every day as human drivers, which we take for granted, are actually very complex, even to us human drivers. And then translating that to an autonomous system poses additional challenges, which is some of the kinds of things that we have to deal with and think about when we're building these things. But before we jump in, I'm just going to briefly introduce myself again. I think Griselda did a much better job at that than I could ever do. But yeah, like I said, my name is Edozie Eze. I'm a product manager for autonomous vehicles in NVIDIA. And my role is primarily to lead the development and deployment of our active safety systems. So this includes all of the safety systems that kick in when there's a risk of a collision, for example, and triggers, say, automatic braking or automatic steering. Over the last decade or so, my career has spanned a number of different industries. So I started my career in the oil and gas industry, and then moved over to enterprise software development, and eventually to AV, where I am now. Outside of work, I am a proud father of three and a husband. I love soccer. I coach my kids' soccer team. And I really just enjoy mentoring young professionals and doing whatever I can to help other people grow in their respective fields. So as we move on, now that we've covered that part, as we move on, we're going to explore the agenda and dive into the meat of the actual presentation. All right, so there are a couple of different takeaways that I would really like to leave you with today, and that's what's covered in the agenda. So first of all, we'll get a brief introduction into the complexity behind AV decision making. So how does it actually make these decisions? How do we prioritize the decisions that it makes? And then we'll talk about the architecture, the overall architecture. So we'll walk through from all the way from the back end. So when we actually see or sense our environment, what does that look like in terms of how we predict what we're going to do or what the AV is going to do, and then translate that into the actions that the end user, namely the driver or the passenger, or the other people in the environment, how they interact or how they observe the AV maneuver. And then we'll dive into sensor fusion. So this is really the most or the more technical part of it. We'll talk about how the AV creates a 360 view of its environment and how it's able to understand this environment and how this now leads into the decisions that it takes, right? And then finally, we'll look at some real life examples. So in this part, I picked a couple of examples, some of which I personally have worked on throughout my career, and we'll dive into that a bit, just for you to see how all of the theory relates to a real life practical scenario. Okay, so we'll start this with a quick question, right? And I don't expect an answer from the audience, but just this is something to think about. I'm sure everyone here, or I would assume that most people here at some point have either taught someone, maybe a child, how to drive, or learned how to drive themselves at some point in their lives, right? So if you look at this picture as an example, where you have an adult teaching a child how to drive, the question here is, what would you do next in this case, right? It seems simple enough. So you're driving, you get to a stop sign or stoplight, you stop, and then the light turns green. So what comes next? Now, there are a couple of factors here. First of all, there's a car in the adjacent lane that looks like it might be coming towards us. There's another car next to it in our lane that looks like it's driving away from us. Also, the light just turned green. There's a pedestrian that looks like they may be crossing the street, or maybe just walking down the intersection or the sidewalk. So there are a number of different factors, right, that you have to take into consideration before you take the next step here, whether you're going straight or turning left or right. And this is seems like such a simple task, but when you are, as in this picture here, teaching someone else how to drive, or when you're learning how to drive, you get a sense of all the different things that you have to do. and you do all of these things happen simultaneously when you're driving, right? It's not sequential. You're thinking about each of those different things around you at the same time in order to make a split-second decision. So AVs work in pretty much the same way, as we're going to see, in upcoming slides. So let's break down the steps from the previous slide, right? What's really happening? The first step here is what we call the perception. So essentially, that's exactly what it means. You're perceiving your environment and you're trying to understand your place in said environment, right? The next is a threat assessment. So you need to understand all of the risks, and you need to understand or predict what will happen next outside of your car. As humans, we typically rely on not, our eyes and ears, yes, but also some other types of two-way communication, right? And this could include, communicating with other road users, either verbally or non-verbally, with things like eye contact or honking. You also need to read the signals or signs on the road. For example, you can interpret the red light as a stop and the green light as go. And also you make certain assumptions of what other drivers on the road are going to do based on your own assumptions of what you would do if you were in their place. So again, there are lots of things happening in the threat assessment stage. Next comes decision making, which is, what should I do? Now, after you know what other people would do, or first of all, you know what you've seen, you know what other people would do or what you assume other people would do. Now it's about, what do I do? So this is where you decide, do I keep driving? Do I make a left turn, right turn, etc.? And finally, you have the action, which is simply just, performing whatever action it is you decided in step 3. So all of these things are what we want the autonomous vehicle to do exactly in this sequence. So let's see what it looks like on that side. So essentially looks like the same thing. It's the same exact steps, only by slightly different names. So first of all, your perception, what do I see? The AV sees the things around itself using sensors, different kinds of sensors like radar, LiDAR, camera, ultrasonic, whatever those may be, depending on what the need is. And then after that, you have prediction, right? So again, what would the road user do or what would the other road users do in this instance, right? So we use a bunch of different algorithms, right, to forecast what each object, not just the environment as a whole, but what each object that the AV can see will do at any given point in time. And this is dependent on several factors, like the current position of the object, the current speed or the velocity of the object, the current angle even of the object. So these are all things that the AV needs to recognize and understand. And then it takes an aggregate of all of those to create what's called a 3D world model. And this world model is essentially what the vehicle sees, and that's what then goes into planning. So the planning part, again, similar to what a human would do, it's essentially planning its next action or planning its path. And finally, it goes into control, which just actuates all of the whatever control mechanisms are in the hardware. So your steering, your throttle, brakes, etc., whatever those may be. Again, every single one of these steps happens in real time, right? Over and over and over again, hundreds of times in a few seconds. You can have, hundreds of iterations and hundreds of decisions being made simultaneously at the same time. So this creates a very, very complex system. And there's a lot that goes into it, just basically being able to see a world, of the AV being able to see the world around it and make these decisions. And that's actually what we're going to explore in the next slide. So first of all, what is sensor fusion? So let's talk about sensors and how the AV sees its environment. At the core of the perception system is a combination of sensors, right? These sensors are the eyes and the ears of the AV system. And this typically comprises of things like cameras, radar, LiDAR, ultrasonic. Again, these are the most common types of sensors that are used in the industry. Each of these has different strengths. For example, radar can measure the distance and speed to an object. LiDAR gives you an accurate 3D shape and a range to that object. And cameras offer a rich visual detail. So in this visualization that's shown on the screen, for example, right, the red vehicle there is the AV, which we'll call the ego vehicle. And each of those boxes represents how it sees the world. So each of those boxes represents an object. And that object could be a car, it could be a pedestrian, it could be sometimes non-classified objects, or it could be things like traffic lights, traffic signs, etc. each one of these things, or each one of those boxes, corresponds to an object which has its own unique properties. So each one of those boxes ideally would tell the AV what it's looking at. So is this a pedestrian? Is this a car, etc.? It would tell it what the velocity is. So that means, is it traveling straight? Is it traveling perpendicular to us? Is it about to cross the road? All of those types of properties. And this is what the 3D world model that I talked about in the previous slide looks like. This is the map that the AV creates around itself. And at every point in time, each one of those things is a reference point to whatever the AV is going, whatever action the AV is going to take when it's faced with when it's faced with a decision. So the sensor fusion combines all of the inputs from the radar, from the camera, from the lidar, and any other sensors you might have to create a single coherent world model. Now, this is never perfect, right? Sensors can be noisy, they can be occluded, they can be confused by edge cases like reflections or fog. But this is really the foundation of all of AV, right? Before you can decide, or before the system can decide anything, it needs to have an accurate or a confident enough map around its environment to be able to make said decision. Okay, so let's dive into how fusion works. This is an example, a very simple example, right? So if we go from left to right, we see you and I as human beings looking at this, we see a pedestrian, a person just walking down the street or walking on the sidewalk, right? The first step for the AV here is the object detection. So it needs to be able to detect that there's something there, whatever that thing is. And all of the sensors detect that thing in different ways. So the camera takes a video or an image, or like a rich image of it, right? The radar takes a radar measurement to measure things like the velocity, the current distance to the object, and what direction it's moving in, and things like that. And then lidar creates a map of the object itself and the area around, or the environment or the surrounding around that object. Each of these sensors measure all of these segments or all of these signals individually and independent of each other. The next step is they pass this information to what we will call the fusion box or the fusion module. And this is where the processing happens, right? So depending on whatever the fusion architecture is inside this box, it processes each of those individual signals. And what comes out at the end of it is an interpretation of the AV's world model. So in this case, what gets spit out at the end of it is, this is a pedestrian with XY velocity, XY position, and we know this with in this case, a 94% confidence. Now, oftentimes you're not going to have, the system will not have 100% confidence, right? So that's pretty rare, not just in AV, but really in any a software system, right? So there's always room for errors. So what you do is you have different confidence thresholds for different environments and different types of objects. And this is how we make decisions based on what those confidence values are. But the summary is, we take in the raw data, or we take in the object. This object gets fed into as raw data into all of these signals that gets fed into the fusion box, and the fusion box creates the 3D world model. So imagine this happening over and over again, hundreds of times every second, and not just for this one object, but for all of the objects around the AV, the front, back, rear, whatever that might be, right? So it creates an aggregate of all of these things. And this is constantly happening all day, like all the time when the AV is active and it's driving. So that just gives you a sense of how complex this can be and how many different things that the system needs to consider when making some of these simple decisions. Okay, so what does designing a perception system look like? Now, there's a lot that goes into it, but there are a few fundamental design considerations that we need to take when designing any perception system. Again, just to reiterate, this is one of the key components of any AV system, because if you misinterpret the world around you, everything that happens after that point is bound to be error prone, right? So there's always a risk down the line if you don't fix what happens upstream at the perception level. So that's why it's important to choose the right design or to adopt the right design principles when building a perception system. First of all, you have to think about how each sensor interacts with or complements each other, right? So for example, like I said earlier, radar sees the velocity well, but it struggles with object type. LiDAR gives you a great shape information of the environment, but it doesn't give you velocity. So you need to be able to play off of each of these weaknesses and the strengths of each to create a great world model. In addition to that, you need the right number of sensors. So ideally, you want to have a 360 coverage, and you want some type of overlap between the two so that you don't have things like blind spots, right, in your system. You also need to have the right number of sensors. You don't want to just overcrowd the system with too many sensors, because that's not efficient. So you need the right balance of both of these things. Now, the second thing you need to consider is latency, right? So you need the right time synchronization to prevent, for example, a temporal drift between two fast-moving objects. So what does this mean? It means each sensor, so the radar, camera, LiDAR, each of those things operates independently of each other, right? So this means they have things like different frequencies or different frame rates, right? And this means that information is gathered around the AV by each of those sensors at different rates. And so why is this a problem? So I'll give you an example. Let's say, imagine there's a car in front of you and the car brakes suddenly, right? LiDAR sees this at a time of t plus 30 milliseconds. Let's say radar sees it as t plus 40 milliseconds and camera sees it as t plus 90 milliseconds. Now, from the point of view of each of those sensors, they saw this same object at different times, right? What that means then is if you pass all this information into your what we call the fusion box, if you don't make any corrections or if you don't apply any corrections or normalization, you could potentially end up in a situation where the system interprets each of those different signals as three distinct objects. So what happens then? So instead of having one car braking in front of you, you have three. The vehicle would react much differently in each of those cases. Or in a worst case scenario, because of those errors, you might end up losing the object completely, which in some cases is even worse. And finally is the actual architecture of the type of fusion method you want to use in the system. So in this case, there are a couple of different methods, right? There's what's called the object level and the low level fusion. So the low level fusion or the raw fusion is where the fusion module takes all of the individual outputs, component outputs from each of the sensors. So instead of taking a complete camera image, it takes the camera pixels, and then it takes the individual signals from the radar instead of taking the complete radar output, right? And all of the processing happens inside the fusion, and it gives you the result of the car or the person at the end of it. Now, this is great in certain applications, right? Like if you're doing maybe like a large-scale DNN training, as an example. It's very, very, it's usually has the potential for higher accuracy and more robustness than the object level fusion. On the flip side, though, it's a lot more expensive. So you require way more computational resources to be able to run this. It's also harder to debug when there's a problem. On the other hand, object level fusion does the opposite, right? So instead of taking the individual signals from each of those sensors, each of the sensors processes the image or the object individually, and the fusion takes the aggregate of all of this and gives you a fused object at the end. Again, the pros of this is it's much cheaper, it's much faster, it's easier to interpret, and it's actually used a lot in day-to-day AV systems. The cons is it's limited by weaknesses so if you have a weakness in one of your sensors, you're more likely to have a weakness in the overall fused object as a whole. So again, these are just a few examples of some of the things that we need to consider when building fusion. Of course, there are tons of others, and I rely heavily on perception experts and perception engineers to do all of this work, but this is just kind of a tip of the iceberg of the kind of work that they do when they're building out these types of systems. Okay, so let's talk about failure. Another key design consideration to consider when you're building an AV system, and I would argue like any software system really, or any technology stack, is you are going to have failures, and you need to prepare for that, right? So we're gonna talk about a few different failure modes and all of these are things that I've seen myself in the field, right, during development, right? And these are some of the things that we think about in the beginning of the whatever AV project you're building. They will happen, without fail. And when they happen, you just have to find ways to deal with them and ways to fix them and improve them going forward. So the first example here is a misalignment between sensors. So imagine what we described in the earlier slide, where you have the camera sensor and you have the radar sensor. The information is arriving at each of those sensors at different times or different relative times, and we have to process them. And how we process them is we need to measure the distance from each of the sensors to the object, and we need to measure the distance from one sensor to the other, or the relative distance from one sensor to the other. So if one of those sensors is not aligned properly, that changes that, right? And if we don't account for it, that can lead to inaccurate estimation. For example, inaccurate estimation of a distance. So imagine in the real world, what that could potentially lead to is a case where, let's say there's a risk of a collision somewhere, and the vehicle measures the distance at which you're supposed to stop, or which it should stop automatically. If you calculate the distance to the object wrongly, and it's actually closer than you calculated or you imagined it, you end up hitting the object, right? So that's just one example of what could happen in that case. Another thing that could happen is duplicate or missed object tracking. And this usually happens sometimes when you have degradations in one or more of your sensors. So this means, for example, that one sensor, for whatever reason, goes offline for a certain period of time. So when that happens, again, you don't have enough information to process the things that you see. And the sensors that you have remaining will probably not give you the most accurate measurement, or in some cases, they wouldn't even detect it at all. And of course, this can lead to some dire consequences. And finally, false detections. This is this can be very common, especially earlier in these projects. And this is a problem that we continuously try to solve across many different stacks. And there are different forms of false detection. It can be due to different reasons. And as an example, it could be due to shadows or occlusions or reflections, right? So imagine you're driving by a busy street or a street that has buildings on either side, glass buildings on either side, right? And there are cars on both sides of your vehicle. Now, all of those cars are going to reflect to either your left or your right, depending on which side that you are. If your perception system is not robust enough, it could potentially detect one of those reflections as a real car, which means that if the AV needs to make a decision that's based on the presence of another vehicle, it will consider that. And again, this would definitely lead to the wrong behavior, and in some cases, safety risks and safety issues. So the summary says, understanding all of these risks is crucial. So as we move towards creating even safer autonomous vehicles, as we move towards scaling the autonomous vehicle market, these are some of the things that we really need to think about, and some of the failure modes and risks we need to be aware of as we build out these systems. Now, let's talk a little bit about how we mitigate some of these risks and what those safety nets are. So as I mentioned before, we are going to fail, and we recognize that early enough in the project. But when we fail, we build to fail safely. So what does that mean? So let's take an example where the AV is uncertain of its environment for whatever reason, for one of the reasons I mentioned in the previous slide. So we don't have enough sensor data, or there's a misalignment, or the objects are not there, or something, right? So first of all, we need mechanisms in place to understand that we're limited, right? So we need to be able to recognize when one sensor or more sensors are down. we need to define what we would do in those cases. We need to define what happens when there's an occlusion that we really can, or the AV cannot interpret, right? So what happens in these cases is we have built-in failure or safety nets in the system. As an example, we have redundancies. There's lots of redundancies in all of the different steps. There's redundancies in perception, there are redundancies in the planning, and even in the controls. So all through the stack, you have to have redundancies in place, because it's inevitable that one of those things will fail at some point. And you want to be able to build a robust enough system that that really doesn't matter in the end. You're still able to take the right action. So really, what does this mean, right? So as an example, if you live in a place like, or in any major city where there are lots of AVs on the road, right now, take a city like, say, San Francisco, as an example. I'm sure you might have seen either some videos online or news articles, or maybe even you witnessed this live, where you're walking down the street or just going down the street and you notice one of those AV vehicles with the big LiDAR sensor mounted on top of it, and it's just stopped in the middle of the road, right? There's a reason for that. Now you could look at that and say, this is obviously a terrible system. A human driver would never do something like that, and you're right. But there's a reason behind that. The reason for that is there's likely a failure in maybe one of the sensors or the controller or the planner or whatever that is, and the vehicle stopping there is actually the safest thing it can do. So it stops there, and then there are other mitigating things like human fallback mechanisms, like remote operations, as an example. And the cars that we're producing today, which people actually own, a lot of those, we don't have any fully autonomous driving cars today that customers are actually driving. So in those ones, you usually have a human in the loop. And what we ensure is that whenever there's any kind of uncertainty, we fall back to the human and make sure that they take control of the vehicle. So these safety measures are not just theoretical, right? We're actively shipping all of this daily, and this is really the core of at least the safety aspect of autonomous vehicles, both now and in the future. Okay, so now we're going to look at some examples, right? So I deliberately picked these 3 examples because these are some of the quote unquote simplest maneuvers that a human driver can do in everyday life, right? So stopping at a crosswalk or a stop sign, making a left or right turn maneuver at an intersection, or merging onto a highway. So we'll take a look at these one after the other, right? So let's start with stopping at a crosswalk. Now, as a human driver, again, this seems like such a simple thing to do. You're driving, you get to a stop walk or stop sign. There's a traffic light you have to obey. It tells you where to stop. You stop there and wait for the pedestrian to stop, and then you keep driving, right? Simple enough. Now, an AV in this case, so the Eagle vehicle, first of all, must do a few things. First of all, it must detect the traffic signs and road markings. Again, we've already established that this is not a simple task, right? So we're going from all of the sensors through the fusion, through perception sensors, fusion, and then downstream to the world model creation, right? So it needs to be able to tell the different traffic signs. It needs to be able to tell what the differences are and what actions it's supposed to or not supposed to take. It also needs to be able to detect the road markings. So if you have a stop walk or crosswalk, there are usually road markings on the road. And typically in a lot of cities, you have a line showing where the Eagle vehicle should stop or where the driver should stop. So the AV needs to be able to detect that. Next, it needs to be able to detect the pedestrian. It also needs to predict the pedestrian's intent to cross. Now, this is a lot more complicated than it sounds, right? Again, for a human driver, you look at someone, you can intuitively tell that they're either about to cross the road when they haven't crossed, or that they're not, or maybe they're walking, on the sidewalk, or even standing still or whatever. So the AV needs to be able to do that as well as humans do. And again, this is not a simple task. There's a lot of algorithmic processes that go into this, right? From the perception to the planning. It needs to be able to handle uncertainty, right? In those cases, so imagine the pedestrian in this case was standing behind another car, right? It's partially occluded, so we can't really tell what the body shape, or the AV can't really tell what the body shape of the individual or what the pedestrian is, right? That's just an example of one of many examples of what could lead to uncertainty. And we need to consider a lot of edge cases. So all of these things, again, is what the AV needs to do at that instant point in time, hundreds and hundreds of time in a matter of a few seconds, for just stopping and going. So let's look at the next example. The next one is making a left turn at an unprotected intersection, right? So while making a turn, again, similar to the last slide, there's a number of things it has to consider. First, it needs to accurately judge the gaps in traffic, right? This involves assessing both the distances of all of the moving cars, the speeds of all of the moving cars, and the relative positions, right, to the ego vehicle and to other vehicles around at the intersection, or on all of the lanes, right? So the AV needs to be able to determine how safe it is, where everything is, and really how the environment all kind of works together to create all of this, right? So imagine, waiting too long, right? So if it waits too long at the intersection, the cars that, with the space we have might close, because cars might start moving. If we move too quickly, this would also lead to risky situations, because there's always risk of collisions, right? Next, we need to predict the speed and the intent of oncoming cars. So this is crucial. So we need to know, when the car is coming, is that car going to turn left, or is it going to turn right? Is it going to keep going straight? These are all the things that I need to consider as a human driver, and these are also things that the AV needs to consider while it's making that turn. And then finally, it needs to confidently time the maneuver, right? So this means that, especially in heavy traffic, the window of opportunity to turn a lot of times, especially when there's no traffic lights, it can be small depending on the amount of traffic, right? So the AV needs to be able to accurately judge exactly when it's safe to go and when it's safe to stop. And another thing to add here is, things can change very quickly. So imagine the vehicle is turning, it already has a planned path, right? And it goes into the intersection, and right as it's at the intersection, a driver that was previously stationary decides to speed up for some reason. So in that case, it basically needs to replan its route. It needs to replan its path, and the next course of action. So it should be very adaptable and very precise in making this turn. Finally, we'll look at merging into a highway. So this used to be one of my least favorite things to do when I was learning how to drive, trying to determine or remember the difference between a decelerating and accelerating lane. But again, this is another example of what the kind of areas that the AV needs to navigate. So when it comes to merging, the vehicle really needs to skillfully adjust its speed and position correctly in the lane, right? This is necessary to safely adapt to the traffic. It's necessary to safely adapt to the things like the speed limit of where it's coming from versus where it's going into, because typically when you're merging onto a highway, you're moving into a higher speed limit. And maybe in some cases it could be lower speed limit depending on where you're merging from, right? So the AV needs to be able to consider all of these things. There's also another problem here, and something that we as human drivers often deal with. So imagine you're merging into a very busy highway. Again, the room with which you have to maneuver is really small, right? When you're at the intersection, because you have people, let's say rush hour, everyone's trying to get to work, or maybe driving home, whatever that might be. Everyone's in a rush. There's not a lot of space. So a lot of times what happens is we rely on the generosity of other drivers on the road to be able to make that merge or make that turn, right? So we communicate with other drivers. And how do we do this? As an example, we use eye contact, right? We use hand gestures. And oftentimes, we do this. So now think about this problem, right? Think about an autonomous vehicle that doesn't have a driver. How then would the system navigate such a situation, right? Where we need to communicate with other drivers, but the system really doesn't have this means of communication, kind of this eye to eye, in this case, this eye to eye or eye contact interaction. So this is a problem. This is actually a real problem and an interesting one to solve, right? And this is, again, one of many edge cases and many types of problems that, as we try to improve the robustness of all of these systems across the industry and across different manufacturers and builders, these are some of the things to keep in mind. Okay, so we're going to talk about more examples, but these are actually, I picked a couple of examples of things that I've had to work on. So I worked on one of the active safety systems that I lead the development of is something called autonomous emergency braking. And this is essentially a feature that brakes the car, like the name suggests. It brakes the car automatically when there's a risk of collision. So imagine you're driving at a high speed or a low speed on the highway. There's a car in front of you and you don't have enough time to react. So maybe the driver is distracted or the driver for some reason is incapacitated. If we get to a certain point and the driver still hasn't started to brake, the vehicle recognizes that there is a risk of collision and it applies automatic braking to bring the vehicle to a stop and avoid collision, or at least mitigate that collision and reduce the speed at which that would happen. And this is actually a real feature that it's very popular amongst different car manufacturers now, and it's something that we're starting to see more and more of it go into different vehicles and different car lines, right? It's a life-saving feature. On the other hand, though, it can be a risk, right? So this first example is something that I myself have dealt with in the past, where we've seen reports from test drivers of the system or the AEB feature just braking for non-existent objects, so ghost objects in this case. So imagine, again, driving down the street or driving down the road at 50 miles an hour and all of a sudden your brake just triggers and you don't know what happened for apparently no reason. So this is bad, right? This is very bad. And obviously, and the caveat here is this is actually a problem that we've worked for a long time to solve, and a lot of manufacturers, a lot of AV developers have worked a long time to solve. But like early enough in any project, this is something that we see, and it's a matter of kind of improving and the perception and the planning stack. But anyway, in this case, what we saw was that the vehicle was actually braking for metal objects on the road, right? And these metal objects can be things like manhole covers, for instance, or metal guardrails. So what we found is radar, because of the way it works, it doesn't really work very well in environments where you have a lot of metal, right? Because it interferes with the radar system. So what we found is in some of these cases, we would have a false brake, or the vehicle would have a false brake and on this metal object, and we looked at it and the radar says, hey, this is a pedestrian, even though it's a guardrail or just a manhole cover or a piece of metal on the road. So this is something that some other AV manufacturers, like outside of projects that have worked on, these are real life scenarios that we've seen in the past, and these are case studies that we did. And again, going back to the design of the perception systems, these are some of the considerations that we took when designing our own system. So making sure that the DNN is properly trained, the radar system is properly trained to classify all of these types of road surface features and things like guardrails and other types of features that are things that we don't want to react to. So another example, again, from AEB, is again something that happened in real life. We've seen this across different car lines, and this is another problem that my team and I actually worked on helping solve. So in this case, what happened was the Eagle vehicle was driving through an intersection, got to a green light, and as we're driving past the green light, there's a truck in the adjacent lane that's driving down through the same intersection, but because that truck sees a red light, it stops. Now, unfortunately, the truck was traveling at such a speed that it had to brake suddenly. And then what happened was when the truck applied its brake and stopped, the AEB system in the Eagle vehicle didn't notice this on time, and it's essentially just applied the AEB braking and just stopped the car in the middle of the intersection. Again, this can lead to very risky situations because, again, imagine there are cars behind you, other cars crossing intersections, etc. In that case, instead of reducing risk, we're actually we actually would be increasing the risk of collision in this case. So what we found in investigation was something interesting too, right? So the truck is a very large object. And what can happen sometimes, depending on the kind of sensors you're using, and especially with radar systems, is when you have such a large object, we can get some errors that essentially breaks the object into two. So you have the driver's cabin and the trailer behind it. Now these are the same truck, but the way the radar sees it, it sees it as two different objects. And now because the truck was moving at a high speed, when it applied the brake and when it stopped, there's a little bit of inertia. The truck moves back and forth, and because of that movement, somehow the radar interprets this as again, we have two objects, and then the object in the back, which is the trailer bed, it's still moving, right? So when the radar recognizes, or when the radar decides that truck bed is still moving, it raises the flag for collision imminent, and this leads to the planner to react. So anyway, similar to the previous example, one of the things that we do to mitigate this, again, make sure that the radar system is trained for these types of scenarios. Make sure you have the right data sets in there, and also make sure you have the right level of tuning in your planning and control system. So as an example, you take a look at this. If you look at how both objects were moving before they got to this point, your intuition should be able to tell you that these are actually two objects, even though the radar might identify them as two. And then you use your camera or any other sensors you have as a redundancy for confirmation. So using this logic and making sure that you leverage all of these different types of sensors and leverage your planning module, you're able to avoid these types of scenarios or these types of events from happening in the real world. All right, so wow, that went by so fast. We're at the end now. So again, a couple of key takeaways here. First of all, remember that while autonomous driving technology is incredible and it's incredibly powerful, it's not foolproof, right? The complexities of all these real world environments, some of which we looked at in earlier slides, things like occlusions and reflections, these require very meticulous design systems or system designs. Without robust engineering, you can have errors, and these errors can lead to false positives, or in some cases, false negatives, which not only undermine the driver's trust, but also could lead to safety risks, which I think is an even bigger type of risk, right? Next, thoughtful design is crucial, right? We need to focus on precise things like, we talked about precise time alignment for the sensors, making sure we have the right sensor calibrations, making sure we're picking the right types of sensors and the right combination of sensors, right? So all of these things are key. Selecting the right fusion architecture is key. And I always look at this like any kind of product development, right? You always start from the problem that you're trying to solve, and then you think of all the iterations or all the versions of that problem, all the edge cases, and make sure you build for them, and you build for them at the component level, right? Which means that you build for them from the beginning of the stack, right? From your perception, making sure you have the right sensors, the right architecture, the right combination, things like that. So always think about the problem you're trying to solve and always tie that back to what you're doing at the very beginning. And finally is testing. I can't overemphasize the importance of testing. So we need to test in all kinds of environments, simulated environments, using real world data. Make sure you're stress testing as many possible edge cases as you can imagine. In areas where you can't just go out and test, in areas where you can't go out and just test an open road, you make sure you have things like fault injection, right? And what that means is you artificially limit the capabilities of the system. So take one of the sensors offline and see what happens to the rest. So you do that over and over and over again, thousands of times, training your models, making sure you're validating over and over again. So this is really, I think this is, in the iteration cycle, this is the most involved part of AV development, right? Because you deploy early and then you fine tune and fine tune and fine tune and fine tune. I can't stress how important that part of AV development is. So if you ever, if you're in a place where or if you ever find yourself in a place where you're doing AV development, this is definitely something, regardless of what your role is, this is always a key area if you want to have impact to focus on contributing or focus on learning about or help scale. And yeah, so that's all I have for today. And again, keep these principles in mind, keep this at the forefront. And if we do this, we can continue to develop autonomous driving technologies safely and and happily. Thank you.
All right. Thank you so much, Edozie, for giving us such a compelling look into the future of autonomous vehicles. This has been truly enlightening and has definitely sparked our imagination. Now, I've gathered a good 36 questions. I don't know if we'll get through all of them, but I hope that we can get through a good portion of them. So
Well,
I'll
wow.
take the
Okay.
presentation off, and we'll bring the
Sure.
questions up onto the video so then we can see them and go through them. So just give me a second.
Okay.
The very first one at the very start, Peace was asking, what are some of the challenges you've encountered as a product manager throughout your career? Can you speak more to how you got to where you are now?
Yeah, that's a loaded question. That's a lot of questions, right? But yeah, I'll try to answer. Okay, so the first one, some of the challenges. So I think there are lots of challenges you encounter as a product manager, right? But for me, I think the biggest one is ambiguity and learning how to navigate ambiguity. Because one of the reasons you have product managers in almost any organization is to help define, not just define the product, but help clarify those ambiguities, right? And that comes from the fact that you have so many stakeholders. You have your customers, you have engineers, you have, whoever, like your internal users, whatever that might be, right? Everyone has different, you might be working towards the same goal, but everyone has uh, different needs and different priorities. So learning how to balance all of these, learning how to deal with that type of ambiguity is very important. And for me, I think there are different ways of doing that. But I think one way I can think of would be I would say being very, very collaborative, right? Because again, you're dealing with so many different people with different needs. You need to be able to be empathetic. You need to understand the needs of each of those, because at the end of the day, as a product manager, they're all your customers, regardless of who the end customer is. So being able to understand what each of your customers need and being able to tie each of those things to the final goal and product is, I think that's the most important thing. Because one thing it helps you do is to, create some clarity and prioritization. So,
Mm. Thank you so much. I'll show us the next one from Chanel. How does cybersecurity come into play when leading design and development of advanced security systems? Are there ever conversations around potential hacking, sensors, and the navigation of crashes?
the short answer is yes, right? I think for any system that you have that's online, any software system, there's always a risk of breaches, of security breaches, right? This isn't just peculiar to the AV industry or AV stack. So when it comes to designing and deployment of safety systems, for example, we have an entire safety team whose responsibility it is, or part of their responsibility it is to do that, right? So it's safety in terms of not just safety to the user of the vehicle or the driver of the vehicle, but also the safety of like what you described here, right? Yeah, prevention of potential threats and things like that. So personally, I haven't worked directly on those types of systems. I have worked adjacent with the safety teams, and I know that these are the types of problems that they try to solve on that side. Similarly, again, to what you would have in any software stack, right? So I think there might be a couple of people, cybersecurity experts on the call that might even be able to answer that better than me. But yeah, but the short answer is yes, these are definitely considerations that we take.
Fantastic. Thank you. All right. Crystal, I believe, asked, how do you navigate the complex landscape of local, state, and federal regulations?
This is a tough one, right? So we have to work around regulations everywhere, right? And I mean that's one of the reasons why, for example, in some city, well, one of many reasons why you have AVs prevalent in one city versus another, as an example, right? You have to deal with those regulations, and the truth is, again, going back to your design, right? When you design these systems, you have to design for those types of environments or those types of rules and regulations. Just to give you an example, I take active safety because that's where I have the most domain knowledge, right? Um, we have something called, certifications and ratings. So certifications are worldwide recognized tests that you absolutely have to pass to even have the AV system on the road. And these also tie into our KPIs. So to give you an example, we have a certain KPI for the number of false positives or the false disengagements that we allow in the system before we allow it on the road. We also have some what's called ODD restrictions. It's got like operational domain deficiencies. I think it skips my mind. But anyway, so ODD restrictions are designed for this, right? So there's some functionalities that may be available in some countries and they're not available in others. So we absolutely have to consider all of these. Unfortunately, there's no unified, global regulation. I will say though that this is something as we develop more and more AV features and more AV products. This is actually a problem that there are very skilled people trying to solve this and kind of unify all of those across the board.
That's so cool. Thank you so much. All right. We've got a good couple more. Are you okay to go a little bit over time? It's just approaching.
Sure.
Okay, perfect. So the next question, how are you addressing accessibility with autonomous vehicles?
Yeah, so it goes back to the system design again, right? So there could be different levels of accessibility, and I think what we try to do is like we work from what does the human driver do. It's not so. Let me put it this way: when trying to build an AV system, you're not necessarily trying to build something new that AV does so much better than a human driver, except be safer and more robust, right? It's what are the things that human drivers do today and how can AVs make that better? So we would approach accessibility from that standpoint, right? Who are the users here? Who are the drivers or the passengers, right? So whatever those types of questions or those types of considerations that we have to make in any vehicle system for a human driver, we basically have to apply the same to AV, because essentially at the end of the day, that's what we're building. We're building an autonomous vehicle system that drives itself maybe better or than a human being should. And to answer your question, yes, we would take the same type of considerations that we do in just regular driving cars today.
All right, awesome. The next one, Alex, how affordable, accessible do you think autonomous cars will be in the next 10 years? I don't know if you have a say on that, but
that's a great question. So I'll talk about accessible, right? And when we say autonomous vehicles, I think it's worth keeping in mind that there are different levels of autonomous vehicles. There are autonomous vehicles on the market today, technically, right? So the very famous one or the most popular ones is something like the Tesla full self-driving feature, right? There are people that have that today. So if you own a Tesla and in certain environments, in certain roads, certain cities, you're able to get some AV capabilities out of that, right? So there's so many different. So it's a broad question because there's so many different levels of AV. Now, from the context here, I'm assuming you mean like a full self-driving, right? Similar to like the Waymo vehicles you see on the road with the LiDAR with no driver, right? And the short answer is, I mean, I don't know, especially how affordable they will be, and in terms of how accessible, I think we do have a long way to go, because the biggest thing is scaling this. It's a huge challenge to scale it from one city to another, right? Not just across different countries. There's lots of work that goes into scaling it. So I can't speak to the affordability, but I think it would be more accessible in terms of driver in the loop types of AVs where we have the features in the cars that people are already driving today, but maybe not those fully self-driving ones yet.
Mm.
But I could be wrong, you know. Yeah,
Well, there's all kinds of things going on. So it's 7 now,
yeah.
Eastern time. Do you have a time just for a little bit more, or are you ready to kind
I
of?
get maybe 1 or 2 more minutes,
Okay, one or two more. All right.
and I have to go.
Let's see. Yeah, absolutely. No, I want to respect your time.
Thank
What
you.
kind of data set can one use to learn these skills? This is so cool.
Uh, what kind of data sets? So if you're talking about maybe like or so like training data sets, for instance, I don't have one off the top of my head. I can maybe find an open source data set. I personally, because we have so much data internally, but I'm sure there are open source data sets out there for AV, right? But these are expensive. So a lot of times, the data comes from production vehicles on the road, and vehicle and cars might be also manufacturers might be kind of guarded with what they share outside of the organizations. But I'm sure there are open source options there. I personally haven't worked with those open source ones, and I'm happy to send maybe something I can send you later, Griselda, and you can share it with Michelle or whoever else is interested.
Okay.
I'd be happy to do that.
All right. Thank you. And then last one. Do you think this technology will be used for trucks, planes, and trains in the future? Maybe a silly question.
I actually think it will be used in trucks before anything else, right? And that's simply because of the use case. And I think this is something that some companies are already attempting to do today. And the reason for that is the most challenging part of autonomous vehicle driving is in urban environments, right? So
Mhm.
if you go to like your neighborhoods and things like that, those are very hard to navigate, right? On the other hand, trucks usually drive for the most part on highways, right? So I think that's a slightly easier problem to solve. And I actually think that we will have that in trucks before we even have it in passenger cars. Now, on airplanes and trains, I'm sure we have a very long way to go, especially planes, right? Because I mean, that's simply because of the amount of regulations that go into just pilots, right? And
Yeah.
the number of steps. So I'm sure we may get there one day, but definitely not before trucks or cars.
It feels very outer space approaching, at least, like the
Right.
whole, like being able to fly around. I like sci-fi, so
Yeah. Yeah.
the
We'll
positive
get there
sci-fi.
someday.
Yeah,
We'll get there
eventually.
someday.
All right. Thank you so incredibly much, Edozie, for giving us such a compelling look into the future of autonomous vehicles. This has been truly enlightening and has definitely sparked our imagination. I'm thinking about all these different scenarios, and our chat was absolutely coming up with so many different questions. They were completely interested. I really appreciate you spending the time and sitting with us and creating this slide deck for us to see. I really appreciate your time, and I hope you have a great night. And to the audience, thank you all for joining this fantastic workshop on driving innovation, the future of autonomous vehicles. We hope that this session has given you a glimpse into the exciting possibilities of automotive tech and perhaps inspired you to explore this new dimension of engineering. We'll have another incredible workshop coming up this next week, same time, same place, as we continue our thrilling journey of shifting gears in automotive tech. Please be sure to subscribe and give this video a thumbs up if you found it informative, if you liked it. If you learned something new, take care, and please continue to innovate and explore the boundless potential of tech and your brains, because you guys are boundless.
Thank you.
Take care.